All right, so this is the last presentation for Chapter 4, which means we'll be done with Chapter 3 and 4. Thursday will be a review. All right, Thursday I'll review anything from Chapter 3 and 4, give you a lowdown on what I'm going to expect from you. And then if you choose to, I'll throw a date up on the discussion boards on Blackboard. I'm thinking Sunday night, maybe 7, 8 o'clock, something like that, to review for, an extra review for the exam. All right, so we're going to look at redox reactions, and what redox stands for is reduction oxidation reactions. And in these reactions, there's a complete transfer of an electron from something to something else. Okay, and in our example here, we've got iron solid and copper 2 aqueous, all right, yielding nice. Yielding iron 2 aqueous and copper solid. Now, if we were to see this in a lab setting, we would have a solution of copper, which is usually a blue color. Blue like, actually a bluish like my water bottle. Okay, it's this bluish color. We would drop solid piece of iron in there. And over time, the iron would go into solution, the copper would fall out, and the solution would lose its blue color. Like magic. I have a solution, I drop a piece of iron in it, and the iron turns into copper. What's really happening is that there's a transfer of electrons where iron goes from not being ionized to being ionized and being soluble in water, and copper goes from being ionized to not being ionized and insoluble in water and falls out. Now there is a reaction that we would have been doing in lab, which is the copper reaction that you will do, that you would have saw this happen live. Okay, but again, we're talking redox here. We're talking reduction, oxidation. Okay. So, we're talking redox, which is reduction, and oxidation. Okay, reduction is the gaining of electrons. Oxidation is losing electrons. If I'm being reduced, I'm known as the oxidating agent. Okay, so if I'm being reduced, if I'm undergoing reduction, I'm gaining electrons, I'm known as the oxidating agent. And if I'm undergoing oxidation and losing electrons, I'm known as the reducing agent. Now I know that might not make sense right now, but we'll come back to this. I'm just putting this up there for completeness. The acronyms to remember: losing is oxidation and gaining is reduction, is just that. They use oil rig. Oxidation is losing, reduction is gaining. Or the one I like, Leo the lion goes grr. Losing electrons oxidized, gaining electrons reduced. Okay. So if we go back to our slide and we look at this, iron's going from no charge to +2. It went from 0 to positive. Therefore, it had to lose electrons. 0 to positive, had to lose electrons. So iron is being oxidized. Copper went from +2 to 0, no charge. How do I go from a positive and get to 0? I had to gain negatives. So copper gained electrons. So copper is reduced. Okay. So who cares what's going on? Why does this matter? Here's the reaction. Here's an oxidation reaction, a redox reaction that you did in lab. This was your empirical formula. You took magnesium, you burned it, so you added oxygen, and you made magnesium oxide. Magnesium had no charge, oxygen had no charge, and then when they formed a compound, magnesium became 2+, oxygen became 2-. So oxygen gained electrons and was reduced. Magnesium lost its electrons and was oxidized. So in order to figure out whether a reaction is oxidized or not, we have to look at something called oxidation rules. But here's the deal with oxidation rules. For the most part, if you know the charge by looking at the periodic table, you know the oxidation number. Okay? So number one, if I'm an element in my elemental state, that's what this is up here, I have an oxidation number of 0. If I'm a monatomic ion, whatever my charge is my oxidation number. And if I'm combined with other elements, the sum of my oxidation numbers has to equal whatever my charge is on the compound. And we'll talk about that right now. Okay. So, let's pull that view back up here and take a peek. I've got sulfur trioxide. I have sulfite and I have sulfate. And I want to know what is the oxidation number on sulfur. And here's how I do it. I go back to my little table here and I look at my rules and look for sulfur on here. Sulfur's in group 16. I see a group 17 rule. I see oxygen. I see fluorine. I see hydrogen. I see group 2. I see group 1. I see nothing for sulfur. So I must have to use what sulfur's bonded to find sulfur's oxidation number. So I go back and say, well, is there a rule for oxygen? And I look here at number 5, and it says, for oxygen, all compounds that aren't peroxides, except with fluorine, is a -2 charge. So oxygen, no matter what it's bound to, has a -2 charge as long as it's not O2 or a peroxide, which we won't worry about right now. So every one of these oxygens has an oxidation number of -2. This oxidation number is -2. This oxidation number is -2. Okay? So I have 3, and this is how you should do it. Listen to me. If you do it this way, when we get into the chemical equations, you'll never have to balance them to figure out whether you're a redox reaction or not. -2 times 3 is -6. Okay? Now, if I go back to my slides and I look at general rule 3, the sum of the oxidation number values for the atoms in a compound equals 0. The sum of the oxidation numbers of values of the atoms in a polyatomic equals the charge. Okay? So, when I add this number to sulfur's oxidation number, it has to equal 0. So, sulfur must be a plus 6. Plus 6 with a minus 6 gives me 0. So in sulfur trioxide, sulfur's oxidation number is plus 6. Let's try another one. Let's go over here. All right, we know oxygen's always a minus 2 times 3. Well, not always, but in our case right now, is a minus 2. Minus 6. When I add it to sulfur's oxidation number, it has to be a minus 2. So what must sulfur be in this case here? Rob, you're right. It has to be a plus 4. Minus 6 plus 4 gives me my minus 2. My oxidation numbers have to equal the charge on the compound. Okay, so oxygen, minus 2 times 4 minus 8. Has to equal a minus 2 charge. So what does sulfur and sulfate have to be? Yep, now plus 6 is the right one. Because plus 6 and a minus 8 gives me a minus 2. Let's try a couple more. So we got carbonate, carbon dioxide, carbon monoxide. Oxygen's going to be a minus 2 based on that rule. All right, let's figure out what carbon is. Oxygen, minus 2, 3 of them for a total of minus 6. What's carbon have to be? I need carbon's oxidation number when added to this number down here gives me -2. So what does carbon have to be? We got it. +4. Perfect. All right, let's do this one over here. What does carbon have to be over here? In carbon dioxide. Trenton, don't forget, multiply these together for a total of -4. Take this times the subscript. Oxidation number times the subscript. -4. So what does it got to be? It's got to be a +4. Because the total has to be 0. There's no charge there. Okay. Now for carbon monoxide, I take -2 times 1. Oxygen's a -2, so carbon has to be... Now Trenton, give me your answer. +2 works here. All good, all good. As long as you realize where you messed it up, it's all good. Are we okay with this? Doesn't always have to be oxygen either, guys. We could have something like, let's look at ammonium. Okay, NH4 plus. If you look at your rules on the PowerPoint, hydrogen, number 3, rules for specific atoms. Hydrogen in combination with nonmetals is always a +1. Nitrogen is a nonmetal, so hydrogen's a +1. +1 times 4 gives me +4. The total charge is +1, which means nitrogen has to be a -3. So if there's no rule, for an atom, it should be able to be figured out over here on what it's bonded to. How about for a compound? How about something like Na2SO4? All right, if we go back and we look at our PowerPoint again, group 1, sodium, always a +1. Oxygen in our case is a -2. Now, what I usually tell students is this. What am I waiting on? I am waiting. Not 8. Hydrogen's charge is a +1. +1 times 4. Right here where I have the arrow. For hydrogen, +1 combination. So plus 1 times 4 is plus 4. That's why it's a minus 3. Nope, hydrogen's a plus 1. If I have a polyatomic, what I normally tell students to do is pull the polyatomic on the side and figure it out. Okay, so that's minus 8. That means this has to be plus 6. Because sometimes it gets a little tricky. But minus 2, minus 8, sulfur's a plus 6, plus 6. 1 times 2, plus 2. Break everything down. Plus 2, plus 6, minus 8, and that's our zero charge. So sulfur is a plus 6. So where this is important is to figure out if I have a redox reaction or not. Assigning oxidation is step 1, but do I have a redox reaction or not? So if we take a look at a reaction, let's do the formation of water. H2 gas plus O2 gas, 2H2O gas. I need a 2 here. And I want to know, is the reaction redox or not? If it's redox, there'll be a change in oxidation numbers from the left-hand side to the right-hand side on the same species of element. Now, got to go back to our rules. For atoms in their elemental form, my diatomics, my metals as solids, things like that, the oxidation number is 0. And this is why the fat guy told you you should know what your diatomics are, because now they're back. H2 is a diatomic. I'm in my elemental state. I have no oxidation value. O2, diatomic in its elemental state, no oxidation value. Over here, we're a compound. Oxygen's a minus 2 for a total of minus 2. Hydrogen's a plus 1 for a total of plus 2. And this again is just following our rules on the slide. Rule number 3 and rule number 5. Hydrogen with the nonmetal is a plus 1. Oxygen that's not a peroxide is a minus 2. So, is this reaction a redox reaction or not? And the way we tell is we compare these numbers. And if you follow it this way and keep your totals on the bottom and don't worry about it, you don't have to worry about your coefficients. You just focus on these, and is there a difference? So is there a difference between the 0 on oxygen and the minus 2? Is there a difference between the 0 and the plus 1? And the answer is yes. If there were no difference, then we wouldn't be a redox reaction. But we are. Hydrogen went from a 0 to a plus 1. Oxygen went from 0 to minus 2. So, how do I go from a 0 to a plus 1? I had to lose electrons. How did I go from 0 to minus 2? I had to gain electrons. So hydrogen, Leo, hydrogen lost electrons. I don't know why I made that a Q. It was oxidized. Oxygen went from 0 to -2. It had to gain electrons. Gaining in this case is negative. You're gaining negative, so it was reduced. Now, since hydrogen's being oxidized and ripping the electrons off of oxygen, it is called the reducing agent. So whatever is being oxidized is the reducing agent. And whatever's being reduced, and I don't know why I'm obsessing with putting a Q today, is the oxidizing agent. I'm being reduced. How am I being reduced? I'm gaining electrons. So what am I doing to hydrogen when I rip them off? I'm oxidizing it. That's why I'm the oxidizing agent. Questions on this? If I am a redox reaction, I will have something that's been oxidized and I will have something that's been reduced. If there is no difference, I am not a redox reaction. And let's look at one of those. So if we go back to our acid-base reaction, sodium hydroxide okay, and we say, is this a redox reaction or not? Well, let's look at it. Oxygen's a -2. And if we look at our rules, group 1 is always +1. Hydrogen bonded to a nonmetal is a +1. Hydrogen bonded to a nonmetal is a +1. Group 17, go back to your table. Group 17 down at the bottom here, -1. All right, we go over on this side. Group 1 +1, group 17 -1, hydrogen +1, hydrogen +1, oxygen -2. Now we compare. Is there a difference between sodium's oxidation number on each side? The answer is no. It's a +1 here, it's a +1 here. How about oxygen? Oxygen's a -2. Oxygen's a -2. No difference. How about hydrogen? +1, +1, +1, +1. No difference. Chlorine, -1, chlorine, -1. So this is not a redox reaction. Question on oxidation numbers and how to tell if I'm redox or not. Okay. So you could try sample problem 4.7 for homework. I'll make a note of it on the board right now. Okay, it's just assigning oxidation numbers. You can do sample problem 4.8. Is it a redox reaction or not? Here's a summary of redox, and this is a figure right out of your book. We could try sample problem 4.9. All right. I know I could just hit it. I just want to point out one thing. So at the beginning of the lecture on redox here, we looked at, I place iron and copper and the iron disappears. And there's something known as the activity series. And whatever's on top can be oxidized by what's below. So lithium is the easiest to oxidize. Gold is the hardest to oxidize. Okay. So iron shows up here. Copper's down here. Copper can rip the electrons off of iron. If I were to put solid copper in a solution of iron, nothing would happen, because the iron can't oxidize the copper. If I wanted copper to get oxidized and go into solution, I'd have to put it into a solution of silver, platinum, gold, or mercury. I don't expect you to memorize this or know this or anything like that. I'm just pointing it out to you that the easiest is lithium, the hardest is gold. And if I want to oxidize something, it's got to be underneath whatever I'm trying to oxidize. Okay. And these are just, if you want to look at them, different reactions that undergo redox. Okay. All right. Decomposition reactions, combination reactions, metals and acids, things like that. So, the other homework out of the book, page 199, (4.84 to 4.95). Okay. 4.84 to 4.95. And guys that are in my lab on Blackboard, your next lab assignment set up to be submitted there next Thursday, but it's there for you.